Hello everyone. In this session we discuss about traveling salesman problem. Traveling salesman problem is one of the most popular optimization problem. Here a traveling salesman, he visit the different cities to sell his items. So while visiting cities, he has one objective function that he should visit all cities at once, and he should reach the place where he started, and his objective function, main function, is to minimize the cost. Means at a lesser cost he has to visit all the cities and come back to his original place. How this optimization problem is solved using our local search algorithms, we discuss one by one. First algorithm that apply here, hill climbing algorithm. We all know that hill climbing is algorithm where it simulates a climber who is climbing a hill. Here a climber is nothing but a algorithm. Finding steps is nothing but finding the solutions, neighbor solutions which can take it to the goal state, and it has to find the optimum, best solution. Now I represented this problem where n cities are the input is the number of cities and their distances as a matrix, and solution is representation. Each state represents a permutation of the cities, order of the cities that they are that traveling person is visiting. Objective is he wants to minimize the cost of traveling, and every neighborhood means at every he is generating neighbor states by making a slight changes to this state. Suppose it is 1, 3, 2, 4 is the first tour. In the next tour he may make a small swapping between 3 and 2. First you start from 1, 2, 3, 4, 1, like that we generate new neighbors based on the current state. So these are entire steps we have to follow in hill climbing to solve the traveling salesman. Initialize. First we initialize the cities and their routes with their costs, and we take one tour as the initial starting tour. We evaluate, then we generate neighbors, then we select the neighbor who is giving less cost, and my current state will become the new neighbor state. See, this is the problem. I represented it as a graph where A, B, C, D are 4 cities, and distance between these cities or cost between these cities is given on the edges of the graph. I converted this graph itself as one distance matrix because we are implementing this program and this problem in Python or some other C using arrays. Means this entire graph is, if we represent it in a multi-dimensional array, it is used for us. So you can either use a distance matrix or a graph. Now my hill climbing, how it starts, that it takes a initial tour A, B, C, D, A. It calculates the distance 95. So initial tour. Now next it generates a new neighbor by making changes to this A, B, C, D. Means swapped B, C. A new state is formed as a C, B, D, A, and it calculates the distance as 95. So there is no improvement. Means we have to reduce the cost. Next one. Next is generate another neighbor. Means hill climber while climbing the hill, suppose these are 3 possible steps he has to choose. He choose the step according to his objective function. Your climber has 3 possible steps from the current step. Your first step is generated, that is giving it as a old value. Then he goes for next step. It is also giving old value. Then is swapped C and D. This is a new tour. Now A, B, D, C, A. Original tour is A, B, C, D, A. This is a similar neighbor of this original tour A, B, D, C, A. Now it is giving 80. Means cost is reduced from 95 to the 80. That means we are going in a correct direction. Means here traveling salesman's main objective is he has to reduce the cost to travel all the cities. Update. So now this new tour will become my current state for a next iteration. What I do, again I find the neighbors of this new tour. If any neighbor is giving less than 80, I choose him as a current state. Like this process goes on until there is no better neighbor is found. This technique we call it as a hill climbing technique to solve the traveling salesman problem. And second technique, before that let us see complexity, means how many neighbors, what is the complexity of this hill climbing in TSP is big O of n square neighbors, and evaluating at each state he has to evaluate objective function, that it takes a order of big O n. So it may not give a guaranteed optimum solution, but it can give nearby optimum solution. It may not be powerful like branch and bound or dynamic programming, but it gives a nearest optimum solution, because these problems, other techniques, branch and bound, dynamic program, they are initially they are very they give good results, but as the problem size increases, they don't give that much guaranteed optimum. Then hill climbing is opted for one. So this is the first algorithm. Second algorithm, local search algorithm, we can apply simulated annealing problem on traveling salesman. Simulated annealing, as I told you, it is a concept taken from metallurgy, where a metal is heated for a particular temperature, and after that to achieve a desired position, slowly we reduce the temperature to get the desired output. So as I want to show you one live example of this simulated annealing, because it is applied here in our system itself. Now this is a picture. When I want to format this picture, select the picture, I recolor this picture, I go to the temperature feature of the picture here. You see, when I increase the temperature, picture coloring is also changes. When I decrease the temperature, it is giving a new color. So I stop this reducing temperature. Initially I set at high temperature. This is not optimum solution. My solution means here a viewer who is seeing the picture should feel it comfortable. So what I do, I reduce the temperature. This is a new color. Then I reduce the temperature. This is another color. I reduce the color. So I thought that this is suitable solution so that everybody can see the picture. I stop my annealing process. The same annealing process means here all possible colors are my solutions, are my one. Out of those solutions, as I decrease the temperature, I get a desirable solution. So this same process now we apply in our traveling salesman also. So first we initialize with the new tour, and then we take the tour and we set temperature as 1000, and we generate the tours. At each tour, whether that new tour is accepted or not based on the cooling effect, like as it reduces the temperature. Here also I cool this one, and where acceptance is dependent on the probability. Like as I said, here hill climbing doesn't allow worse condition, because it climber always going in upwards, he cannot go back backtrack, so he cannot come back. But here in this simulated algorithm, sometimes it accepts worse conditions, but later on it improves itself to reach the goal. Now we formulate this problem using simulation. These are the, again I shown my TSP as a distance matrix. Initial temperature is 1000 and cooling rate is 995, maximum iteration 10,000, and I generation. These are the initial conditions. As like a hill climb, here also I took my first tour as ADB CEA. I calculated my total distance that I got is 125. Then I generate a new neighbor ADCA, it has a 140. Now whether to take this new neighbor, as a current state or not, what I do, earlier it is 125, now it is 140. I calculate energy consumed by this new tour as 15. Whether then I find whether this probability of this new tour will be accepted or not. This means if can I take this new tour as for by next neighbor generation step or not. What I do, I take this value probability e power delta E by temperature. It is giving 985. So less than, generally it is accepted between 0 to 1. So now this tour will become night tour. My next neighbor generation depends on this acceptance of this tour or not. Like this process will continue on until a point where you get the best distance, and it explores all the possible solutions until you get the best distance, and it stops when your temperature is less than or 0.1. Iteratively we do these things repeatedly. So finally we explore all possible solutions by reducing the temperature. Whatever desirable solution, I selected it. How I got this desirable? When my temperature is less than 0.1, or whatever iterations that we formulated as a constraint 10,000, I stop the iteration and I select it as the best option. So this way you can solve a traveling salesman using hill climbing and simulated annealing. Thank you.